So thank you so much for attending this, and thank you for what you all are doing. I'm going to just jump right into this little script that Allie made for me, so thank you for that, Allie. Welcome to the Optimizing Biological Nutrient Removal in Tennessee Wastewater Treatment Plants webinar series. This is the third webinar of the series. My name is Mark Valentin. I'll be hosting your event today. We will be meeting every Wednesday for the next 4 weeks, so I believe we have one more coming up. Few things first that we want to take care of. Please notice that you all have been muted upon entry. This is to help reduce any background noise, but you can unmute yourself and ask questions. Another way to ask a question is through the chat box. The chat box is in the right corner of the screen. If you click on chat, you can type in your questions there, and we will field those questions for you. And we won't be mentioning your name, so feel free to ask any question you like. We want to make sure you all are comfortable in asking questions, because questions that we may not see is what is helpful for y'all. We want to make sure this is a webinar that's beneficial to y'all and in getting you your CEUs. So please send those questions directly to the panelists, but not the presenter alone, as I will not be able to see them while in presentation mode or Grant. So please field those questions in the general chat or the other panelists. The panelists and I will be monitoring the chat box and the Q&A section. We will read them to the presenter at natural stopping points. Also, if you will, let's take time to check the yes or no buttons. They will appear as a green check mark or a red X. Once you have clicked an answer, please also note that you will have to uncheck that button. Otherwise, that button will stay selected. So this is the if you're looking at yourself in the participant section, on the bottom right, you'll see a hand, a green check, and a red X. So when we ask a yes or no question, click the green. I see a couple people have a green check. If you want to say yes, click that green check for us, and you can see it's working. There you go. That's awesome. So once we're done asking the question, please uncheck it so we can leave it open for the next question. The red X is just a way to say no. So these are our ways of saying yes or no in this chat function. Our presenter wants everyone to know that he enjoys your engagement, prefers to be interrupted with questions, so please feel free to unmute yourself if you have any questions that need to be answered immediately. We will also be seeing those questions come up in the chat box, so I'm sure one of us will jump in and field some of those questions as well. We will have three polls for you to answer. The one in the middle will also allow you to take a quick break. We were able to get approved for 1.5 CEUs for each of these sessions for your wastewater license. For folks that are viewing this training as a group, we will need you to email the names and license numbers to Allie Crampton. This is in the chat. If you look in the chat feature, Allie's email should be in there. It's ALLE.Crampton, CRAMPTON@tn.gov, and we will show it off again later on after the session, and she will include you on the course roster to get you those CEUs. This session will be recorded, and we will make it available on our Tennessee Plant Optimization website, along with the previous 2 webinars. Also, if you have Microsoft Teams on your computer and you feel WebEx is running slowly, closing out Microsoft Teams helps WebEx to run more smoothly. So we would encourage you all to maybe exit out of Microsoft Teams if you are feeling that it's bogging you down or you're getting some glitches within this presentation. Next up, we are going to have Bree jump in real quick, and she's going to be talking about the CEUs.
Thanks, Mark. We've had a few questions come in asking about when your CE credits will be posted to your account. And I just wanted to let you guys know that there is going to be a little bit of a delay with that. So don't expect to see those immediately after the webinar ends. There's a lot of paperwork that goes along with that, and it sort of passes through multiple people's hands. But the week 1, everything for week 1 has been submitted, and so I expect those CEU credits to start cropping up in your account, hopefully by the end of this week. So probably it's going to be at least a week to 2 week delay from when you attend the webinar to when you actually see those credits in your account. And since each session was designated separately as far as the board wanted them all to be separate because you guys can attend one or you can attend all 7, those certifications, the certificates that that you'll get will probably be coming out towards the end of the entire webinar series. So those will show up later. But, still feel free to let us know if you have any questions about it. But I just wanted to let you know that the delay is normal and that we have all of your information and it will be submitted. So you will get those CE credits eventually. All right, thank you. I'll pass it back over to Mark.
Awesome. Thank you, Bree. I believe that's how we have taken care of. I think we're ready to go. I'm going to introduce Grant and we'll start. So let me welcome Mr. Grant Weaver for the third session of our WebEx series. Grant has been working with us since 2014 on optimizing wastewater plants across the state. He is a professional engineer and a licensed operator. Today, Grant will be talking about the case studies of actual plants. Hope you enjoyed the presentation. Please ask questions and comments. We all appreciate your engagement, and Grant loves the interaction. Grant, one other thing I just wanted to mention, I won't be the best at making those yes or no questions throughout, so I'm going to be relying on you for those ones if you want to do them.
All right, I don't have any in mind, but thank you for that.
Yeah, I'll give you the presentation right now. You should be good to go.
All right, let's see if this works. How's that? Are we on my screen, covering the full screen with this heron in the picture?
I do see a heron.
All right, well, thanks. Okay, well, when I put this slide together, I didn't realize it'd be snowing in West Tennessee, but it's pretty incredible. Here I am in Connecticut. Our snow melted. We're supposed to get more tonight, but I'm probably 10 or 15 degrees warmer in Connecticut than those of you in Memphis area are right now, which is got to be pretty unusual. Well, what are we going to do today? There's some 60, 65 of you listening in, so thank you for that. Hopefully you're keeping warm. The last 2 weeks I did a session on nitrogen removal and a session on phosphorus removal. Today the plan is to do a review. A lot of the same slides, but at a lot quicker pace as a review. And then the last half of this webinar, I've got 10 case studies in the queue to present. If we get through 5 of them, I'll be surprised. But we will not run out of case studies today, I'll guarantee you that. The next 3 weeks, we're going to get more specific, talk specifically about oxidation ditches, SBRs, and conventional and extended air in each of 3 different webinars. Talk about dialing in nutrient removal and those technologies with case studies for them. So if your facility is any one of those 3 types, I think you'll find those particularly interesting. And then our final session is to brainstorm for some plants that we really haven't visited yet. We've got a few on our list to visit this spring. First week of April, I think, is what we're hoping to do now. And so we'll include those facilities, but if any of the rest of you are interested, let it be known during any of the opportunities. Through the chat box, you can email me. My email address will keep popping up, or any of the organizers, Mark or Bree or Allie or any of us, and then we'll hunt you down. So we're going to have a polling question here to start off. While you're doing the polling question and I kind of gear up, I just ask you if there's anything that you specifically want me to address today, let it be known. You won't be able to do that in the polling question, but you can do that in the chat box. So if there's anything you'd like me to speak to in the next hour and a half, please let it be known. And with that, I think I'll climb up and hand it back to you, Mark, to do the first polling question.
All right, let me open up the poll. I don't have the ability to open the poll yet, so if you either send it back over to me, or you can do it as well.
Well,
Mark, you should be able to grab the ball from him, I think.
Oh, okay. Let me work on that real quick. So do I just right click on?
No, you can literally just put your arrow over the ball that's next to his name and drag it to your name.
Oh. That is awesome. Thank you so much for that. I do love the power. There we go. The poll is now open on a scale. Can you all see that? Oh yeah, you all are jumping in on it. Y'all have about 2 minutes to do this poll, so we'll leave it open until then.
Mark, you probably don't need to leave that open for a full 2 minutes if it's flooded.
Yeah, if it starts falling down, I'll close it out.
Okay.
Give y'all 10 more seconds and then I'll close the poll. Alright, I closed it out. Can you see them, Grant, or would you like me to read them out to you?
I cannot see the results.
Okay, let's see here.
There should be an option that says like display poll results.
Oh, gotcha. Let me look for that right now.
There they are. All right. I can see the results, and the results, I don't know if everybody else can see them, but half the people are right there and smack in the middle, with about half of the rest or about half of them with no answer, and the other half are just a little bit less than middle of the road as far as the knowledge base. So if you hand it back to me, I can take over from here.
Sure thing.
And after you do that, if there's any comments that have come in, let me know, and I will. Let's see, where are we working on that one? So has anybody weighed in on what they'd like special attention today?
There's no comments in the chat so far.
All righty. All right, so the first session we talked about nitrogen removal, so I'm going to give a little refresher on that. I'll run through what I talked about in nitrogen removal. And as Mark said, and as Bree said, and hopefully I've made it clear. I love questions, comments, interruptions. So if there's anything of interest to you, raise your hand and you'll be unmuted and you can speak, or type in a comment. So for nitrogen, there's two steps for nitrogen removal in a wastewater treatment plant. The first step is to convert the ammonia that comes in as influent to nitrate. And there's a certain environment that we want for that to occur. Again, as I said before, the bacteria are not thinking beings. They just react to their environment, give them the right environment, and they will grow and prosper. So for them to convert ammonia, we need an oxygen-rich process, aeration tank. We don't need BOD. In fact, the bacteria that grow on the BOD grow faster than the ammonia-removing bacteria. So we don't get a lot of ammonia removal until the vast majority of the BOD is removed. Great process control tool. If you're removing ammonia, you can pretty much bank on the fact you're removing BOD sufficiently to meet any permit limits. Bacteria that remove ammonia are sensitive to pH and temperature. Not as sensitive to temperatures maybe we've been taught over the years, but very sensitive to pH. If the pH drops below pretty low level, 6.5, that's going to interfere with ammonia removal. Most facilities, once they dial in ammonia removal, are able to maintain it fairly consistently unless there's some kind of a process upset, something weird happens.
I still think we're looking at your screen.
Yeah.
What?
You are not sharing your screen.
Yes.
I am not sharing my screen?
No, sir.
All right. What do I need to do?
If you go up to the top where it says share, you can go from there.
Share.
There we go. Oh.
We'll get there.
Yeah.
Thank you for that. Yeah, you can see my screen. Good. So the second step then is once you create the nitrates, there's very little ammonia left. Now we have nitrates at NO3, so that oxygen's been added to the nitrogen molecule. We want to strip that oxygen off. To do that, we create an environment where the bacteria are hungry for oxygen, whatever the right word is. They need oxygen to breathe bad enough, and there isn't enough free oxygen, which is the easier oxygen to get. So they will do the work necessary to break that oxygen off the nitrate and breathe that. So that happens in an environment with little to no oxygen. We call that anoxic. They do need BOD to grow, which is actually pretty nice because any BOD that gets removed in the anoxic zone as we convert nitrate to nitrogen gas is less BOD that needs to be removed in the aerobic zone. So we're able to reuse some of that oxygen that we put in for ammonia removal. These bacteria are hardy. They're not as sensitive to temperature and pH. However, they are very sensitive, the bacteria that remove this, to surplus oxygen and to an absence of BOD. So what I see in most treatment plants is even though the bacteria that remove ammonia are the fussier, more temperamental bacteria, it's maintaining consistent nitrate removal requires more process control. So there's, let me get into this a little more into the chemistry here, the schematics, and I'm glad you can see this. So the first step is we take ammonia, you add oxygen, and as that happens, the ammonia is converted to an intermediate process, nitrite, and hydrogen ions go into solution which eats away at the pH, and that's buffered by the alkalinity. You saw my first presentation. I like to use the analogy of ice cubes in a glass of water as alkalinity. So the ice cubes melt, the alkalinity decreases, but it buffers the impact of the hydrogen ions. A little more oxygen, and we're at nitrate. So we've completed ammonia removal, and now we still have as much nitrogen in solution, but the oxygen demand of our effluent is less than it was before. So in early days, this was sufficient because it reduced the oxygen demand on the receiving water, the impact, the DO drop in the receiving water. But that nitrogen is still there and still available as a nutrient to support biological growth. So, hence, we're now moving towards total nitrogen removal. Here's some rules of thumb that I use, and they're just that. They're absent of anything better for any particular facility. It's a good starting place. And then from there, you can move forward and dial in and establish your own targets for your facility. So that completes the first step. Then we've got the second step. I just couldn't resist this picture, so I had to figure out some way to put it in once I stumbled across this. And the second step is going to be to convert that nitrate to nitrogen gas, and the nitrogen gas should bubble out in a somewhat controlled manner in that low oxygen tankage or in conditions where the oxygen is low. We want that gas to bubble out, and it bubbles out as real fine bubbles before the wastewater gets into the clarifier. Otherwise, you'll have rising sludge as the sludge in the bottom of the clarifier gasifies. So we want an environment that's strong in BOD and low in oxygen, and then the bacteria will breathe the oxygen off the nitrate. They will use that in their cellular growth. They'll use the BOD to grow cells, and as they do, nitrogen gas is discharged. And in waters that have a tight pH or acidic waters, half the alkalinity is back. It's like a ice cube making machine here. It puts alkalinity back in the wastewater. Again, some rule of thumb targets to get the process started. A lot of BOD, so look at that. For nutrient removal, we're going to see that as an ongoing thing. Nutrient removal requires a lot of soluble organic matter, a lot of BOD that would happen in the first hours in a BOD bottle. The more the better, actually, for nutrient removal. Excuse me. All right, one more little table. Rules of thumb. So we're going to need a fair amount of BOD. If we have 20 parts of nitrate, we're trying to convert to nitrogen gas, and 5 milligrams per liter of BOD for every 1 milligram. 5 times 20 is 100. Be better with 200, frankly. It'll help drive that better. And it'll help you get into anoxic conditions quicker, more reliably. Any questions so far?
Nothing with Q&A so far, Grant.
Okay, hearing none, we'll keep on. So that was the science. Now we'll run through the technology. This, again, is a repeat of the first. And I'm going to run through the MLE process and the SBR process, and then oxidation ditch. Just get us a reminder of how in these processes we're removing the nitrogen, how and where. So the MLE process is a process where there's a low oxygen tank that precedes the aeration tank. The raw wastewater really doesn't do anything for ammonia removal. The ammonia passes right through that grayish anoxic tank, moves into the blue tank. So whatever ammonia came in into the influent or raw waste of the treatment plant, it remains right until we're in the aeration tank. During aeration, that ammonia is oxidized, and the hydrogen ions go into solution. Oxygen is taken out of the wastewater, and we have nitrates. Nitrates are returned to this anoxic zone two ways. One is the return sludge from the bottom of the clarifier will return nitrates into the anoxic zone. But to bring enough nitrates into the anoxic zone, some really smart people figured out that could overwhelm the secondary clarifier. You'd be pushing so much water in and out of that tank as RAS that it would stir up the contents and you would have poor effluent PSS. So they came up with this idea of having an internal recycle which pumps the nitrates back into the anoxic zone. The nitrates now are going into a zone that's rich in BOD, because the BOD of the raw wastewater. That BOD in a non-aerated vessel, tank, allows the bacteria to denitrify, to convert the nitrates to nitrogen gas, and the gas should bubble out in that tank. Too much of an internal recycle rate and the conditions in the anoxic tank will become too aerobic, and that will reduce its ability to remove nitrates. So you'll be putting a lot of nitrates in there, but it'll become, there'll be too much free oxygen for bacteria to breathe. The bacteria will breathe that free oxygen and will not remove the nitrates. If the pumping rate is too low, you'll have pretty much no nitrates leaving the anoxic tank, but if you'd have pumped more back there, you could have removed more from the wastewater stream, so the effluent will have a higher number. It's a little bit of a dance in an MLE to figure out what the optimal internal recycle rate is. So one of the good parameters there is to monitor the ORP in that anoxic zone. And I like to see it typically initial target of about minus 100. I've worked with facilities that get very good nitrate removal with ORPs of 0 to positive 50. But that's where I would typically start, would be about minus 100 as a target. If there's any questions, I'll pause for them. If not, I'll keep going. All right, I'm going to keep going. So sequencing batch reactor, I really like to drive this one home because, I would say the majority of the facilities that I work with that were not designed for total nitrogen removal, we are somehow adapting the concept of a sequencing batch reactor. We're cycling the air on and off in facilities that were designed to have the air run continuously. You'll see some examples of that before this morning's session is over, before another, 2 inches of snow fall on the ground there. So sequencing batch reactor, typically you have more than one reactor, and one or more reactors is idle, while one or more reactors is receiving wastewater. So the reactors fill and draw, and as they fill with raw wastewater, stream wastewater, then it's aerated, and as it's aerated, we're getting ammonias converted to nitrate, and the air is turned off, wastewater continues to come in. Now we've got some nitrates that we've created during the air-on cycle. We've got BOD coming in during the air-off cycle. The bacteria are fighting to stay alive, so they're going to breathe the oxygen off that nitrate and convert it to nitrogen gas. Now there's a period in between that air-on and air-off where it's transitioning. And then when it goes from air-off back to air-on, again, transitioning. So if you have an SBR, or if you're operating a facility to be like an SBR, you're looking for those environmental conditions when you have a good aerobic environment and a solid anoxic environment. And the transition time is it's not wasted time, but there's a lot less beneficial activity happening during those transitions. After you go through a cycle, the water sits, all mixing is turned off. Most facilities mix during the anoxic zone cycles. Not all do. There's pros and cons to that. And then when the air is turned off, it settles. The clean water is decanted off the top, sent to disinfection, and some of the sludge is wasted. And then it now becomes the idle tank and is waiting for its next cycle. So for process control, there's two ways in all of these situations to look at things. There's the environment. How nice of a habitat is that for the bacteria to live? So that's dissolved oxygen, pH, ORP. And then there's also how are the bacteria reacting? So how good of a job have they done? So that's looking at how much ammonia there is, how much nitrate there is, and what happened in that environment. So we can monitor and set targets by looking at both the nitrates and ammonia concentrations in a facility to help us set the targets, the process control, the DO, and the ORPs. And we want cycle times that are long enough to get us to a good, strong aerobic condition and to get and then during the air off to allow that dissolved oxygen to drop, I would say dissipate, to get consumed by the bacteria, so that there's low enough oxygen, then you get into that anoxic state, which you can measure with an ORP. Obviously, if the cycles are so long that you're cycling between air on for 3 days and air off for 2 days, you're going to have many cycles of wastewater coming in and out of the facility, and the cycles are too long. So that's something to keep in mind. That's pretty rare that you would have the cycles so long that you wouldn't have both aerobic and anoxic conditions. Maybe during a storm mode you would do that only. All right, if there's no questions on that, I'll keep going. If there are, I'll stop.
All right, I have a question. This is Bree.
Okay.
As far as those transition times, do you have any data that would give any indication of like a, quote, regular transition time, like how long it takes to sort of switch over between those cycles?
That's a real good question, and I'm gonna semi-evade it, but I'll give you some numbers in my evasive way. So it should be minutes. Okay, you're gonna have 20 to 30 minutes of transition time. You're going to have a shorter transition time going from anoxic to aerobic. In other words, when the air kicks on, the DO climbs pretty fast. DO will probably get close to your target within 5 to 10, certainly within 15 to 20 minutes. The ORP is going to lag a little behind the DO. Why is that? Because dissolved oxygen is a measurement of how much oxygen there is in the tank. The ORP is a measurement of what the bacteria are doing with the oxygen. So the bacteria aren't going to be breathing a lot of oxygen until the oxygen is there. So that activity, there's a little delay. So for that, control, DO is a good control to see when you have the oxygen to a favorable concentration. Now going the other way, from the air on to the air off, in cold weather, okay, you get, if you're in a mountain community and there's a lot of cold water, perhaps in East Tennessee, certainly here in the Northeast and some of the facilities I'll be talking about in northern Montana, has dug on cold water in the winter. Bacteria are moving slower, the solubility of oxygen is higher, so it can take a half an hour, 45 minutes for the conditions to go from strongly aerobic to strongly anoxic in cold conditions. But in either case, it should happen well within an hour. If the transition of going from aerobic to anoxic starts to take more than an hour, you're just going to have a problem with nitrate removal during that cold weather. If you let that go too long, you're at the risk of creating septic conditions. I have a confession, I've done that, and I don't ever want to be there again. So, that's a great question, and it's one that I should have included in my discussion. Is there anything else? Okay. Oxidation ditch. So this is an oxidation ditch actually on the other side of the Smokies. This is in Virginia. Oxidation ditches are very robust technologies. Those of you who have oxidation ditches, you may have your swears that you wish to state at them, but all in all, it's one of the better designs. They have well-designed, well-operated oxidation ditch will go in and out of the aerobic and anoxic conditions as the wastewater goes around the track. So the track going away from us in this picture where all the waves are would be an aerobic zone. And you can see another rotor down there at the far end. It's not running. And with that not running, then the wastewater coming towards us should be able to drive that into anoxic conditions. So you can have, as this little illustration would show, since the wastewater goes around and around the racetrack multiple times before it goes to the clarifier, we're going to have an ammonia zone that we're going to create nitrates as ammonia is converted to nitrates during an aerobic. Then it will go to an anoxic zone. The nitrates will go to nitrogen gas. And if the conditions are right, you should be able to see some gasification occurring in those tanks. And then it goes over and over as it goes around the facility. I think we'll have a whole session on oxidation ditches, and we can drill into that pretty deep during those discussions. But if there's any questions now, I'd be happy to take those or comments. Anybody wants to weigh in, please do. All right. That wraps up nitrogen. So before we go to phosphorus, are we good? It's nice to get our heads wrapped around nitrogen because dialing in phosphorus, to do it well, requires an understanding of the interference from nitrogen. So nitrogen's a good place to begin. Once you get a handle on that, then work on your expertise in phosphorus removal and some of these counterintuitive things. And by counterintuitive, I mean to get better treatment, turn the air off. Not what we are comfortable or used to doing. Learning how to react for the nitrogen removal is going to help in the phosphorus removal. I'm stalling for time to see if there's any more questions. There aren't, so I will jump into phosphorus. So biological phosphorus removal has 3 steps. 2 of them happen in, I like to use the word fermented conditions. They're anaerobic conditions, just short of creating methane gas. So basically any open top tank that's not aerated, if there's sufficient DOD, sufficient retention time, it's going to become a fermenter in fermented conditions. The bacteria that remove phosphorus, remember from the second session, they're very fussy eaters. My analogy is they're like the panda bears in the National Zoo. The panda bears only eat bamboo shoots, the creatures that remove phosphorus in our wastewater treatment plants, they only eat volatile fatty acids. The bacteria that remove nitrogen will eat just about doggone anything. They're like me, and but they prefer volatile fatty acids. So if the volatile fatty acids are there, they will outcompete the phosphorus bacteria. Okay, that's important as we try to dial in all this nutrient removal nonsense. So first thing is we need septic conditions that create volatile fatty acids. Every truckload of septic is chock-a-block full of volatile fatty acids. You get a lot of volatile fatty acids with your septic. You get very few volatile fatty acids out of a well-run anaerobic digester because the digester takes these acids and turns them into methane gas. The volatile fatty acids are the acids in the acid alkalinity ratio. So if you run an anaerobic digester, it's more problematic for biological phosphorus removal. By no means does it take you out of the running, it just complicates your life a little bit. So we need to go short of creating methane gas with these volatile fatty acids. Vinegar is a volatile fatty acid. And the bacteria that we want to populate our mixed liquor to remove phosphorus will feed on the volatile fatty acids. It will feed on them in zero oxygen conditions. If we send the volatile fatty acids into aerobic conditions, then other bacteria will outcompete the phosphorus bacteria and eat the overwhelming majority of the VFAs, and they won't get where we want them to get. If we have nitrates in our wastewater that go into a low oxygen environment with volatile fatty acids, the bacteria that remove the nitrates will eat the majority of the volatile fatty acids. So unless we have a surplus, the phosphorus removing bacteria will be left wanting. So we'll get into that and some of the design technologies. Engineers have come up with ways to work around that. But the first two steps both occur in low or no oxygen environments, fermentive anaerobic conditions, ORPs. I like to see them minus 200 or more negative, minus 225, minus 250, minus 350. And in those conditions, we'll have septic conditions that create the food, the volatile fatty acids, and we got to bring the bacteria, some of the mixed liquor into those conditions. And the bacteria in the mixed liquor, the phosphorus removing bacteria, will chow down on those VFAs. If they do that, they don't grow. They just get energized. I guess the analogy is they would be they'd just be getting fat. And then when they go into the aeration tank, they will take that energy and they will grow. And as they grow, they will suck phosphorus out of solution. So the conditions in the aeration tank, pH is critical. pH is below 6.8. It completely puts a stop to phosphorus removal, biological phosphorus removal. And if it's down 6.8 in the aeration tank, not the final effluent, in the aeration tank for a day, you will lose biological phosphorus removal that day. Bring it back. If it's only for a short period of time, it'll bounce back. It's been down for a week or so. The bacteria are gone. You've got to rebuild the bacteria population. Any questions or comments on that before I get into the technologies that we use for phosphorus removal?
I'm here.
I have a question. This is for you again. How do you recommend that operators are constantly monitoring the VFAs? And if they do monitor the VFAs, is that with the titration? And how exactly do you recommend that?
I'll tell you what, let me put a schematic up here and let's talk about that. All right? So there's two ways to remove the phosphorus in a wastewater treatment plant. One is in the mainstream, so that's where all the wastewater flows through your main tanks. Another would be a side stream, so your return sludge line, a waste line, some kind of a side stream where the raw wastewater, only a part of it's diverted to a side stream. So whether it's mainstream or side stream, there's opportunities, and I'm going to talk through a mainstream one, and as I do, I'm going to get to Bree's question. So if you have a mainstream fermentation process, you're going to have an anaerobic tank where these volatile fatty acids are going to be produced, and then the bacteria that are in and with the return sludge coming into that anaerobic tank or fermented tank will consume the volatile fatty acids. They'll become energized, and then here's the process tool that I would recommend using rather than monitoring volatile fatty acids. I would monitor how much phosphorus is released. Crazy as it seems, this is definitely one of those counterintuitive things. The first step in phosphorus removal is to put more phosphorus in the solution. And that happens when the bacteria either break down and die and they release phosphorus, which is not a good thing. That's a more problematic source of phosphorus. But it also happens when the bacteria are very active, when they consume the volatile fatty acids, and as they do, part of their energizing metabolism is to release phosphorus in the solution. And PO4 is orthophosphate, or soluble phosphorus. So if you measure the soluble phosphorus leaving this anaerobic tank, it should increase from what it was going into the tank. And it should increase quite a bit, 3 times. So no, I know of a few facilities that monitor VFAs, but most don't. Most instead monitor the production, the activity, the performance of this anaerobic fermented tank by how much phosphorus goes in the solution. And we're going to want about 3 times as much as what comes out. Nice thing is, if you have a spectrophotometer, it's a simple, quick test. Soluble phosphorus test takes maybe 10 minutes. So you can monitor what goes in, monitor what goes out. What goes in is fairly constant, hour to hour, day to day, not totally, but fairly constant. So you can establish a target. So if typically it's coming in at 5, say, then I'm going to look for something in the mid-teens. And as long as I'm there, I've got a nice, strong, healthy environment. Again, as I said earlier, there's 2 ways of looking at performance. One is what's actually happening, phosphorus release, measure the orthophosphate. Another way is what's the habitat like, what's the ORP in that anaerobic tank. So you can measure that with an ORP. The phosphorus that are released in the anaerobic tank travel with the mixed liquor, and the wastewater is pushing it all through, goes into the aeration tank. As long as that aeration tank has a nice neutral pH, our target would be 7 or higher. If it gets down to 6.8 or lower, I'm dead for the day for phosphorus removal. So the energized bacteria will take that phosphorus out of solution. Now the phosphorus concentration, if everything's dialed in, is crazy low, 0.05 kind of concentration of soluble phosphorus, which now makes whatever phosphorus is in your final effluent, the vast majority would be as TSS, right? Because if you had a TSS of 10, say, and the concentration of that was like 3% phosphorus, that's a 0.3, and the phosphorus soluble is 0.05. So pretty low numbers can be realized through this process. And there's a number of facilities that are designed this way that are getting consistent effluent phosphorus of the 0.2 to 0.4 range. Now, nitrogen interferes, right? So in the return sludge in this schematic here, any nitrates that are coming into that anaerobic tank are going to outcompete the phosphorus bacteria for whatever volatile fatty acids are produced. So I guess it's tricky. A very brilliant design concept is feed these less fussy eaters hamburgers instead of steak. Feed them BOD coming in as the influent, and the denitrifiers, the bacteria, the nitrates that go flow in the RAS into the now anoxic tank will get converted to nitrogen gas. There'll be fewer nitrates flowing in the anaerobic tank, so you get more bang for the buck for your VFA production in this anaerobic tank. The VFAs that are produced there, the majority of them, because there's fewer nitrates to compete, now they'll be mostly eaten by the phosphorus-removing bacteria, and in the same routine, the soluble phosphorus is released in the solution. It and the bacteria flow into the aeration tank, or under the right conditions, get a better, more consistent removal of phosphorus. So that's a mainstream design facility. All right? If you have one of those, you're lucky in some ways. Otherwise, there's a lot of tanks to start to control, but you have built-in technology. Even more sophisticated way, and this is the Missoula, Montana facility, where it's probably barely colder there than in places in Tennessee today, combines a side stream and mainstream. So let me get into that and explain that. By side stream, we're creating the volatile fatty acids one place. Now, this type of facility, sometimes they'll measure how many VFAs are produced in this. And there is a test, a lab test, to do volatile fatty acids. I'm not sure if there's one you can do with a TNT tube or with a spectrophotometer. Perhaps if there's anybody listening in that knows that, you could just share that you're familiar with that. That would be appreciated. But you can create volatile fatty acids here. So this would be equivalent to septage being trucked into your treatment plant, but at a controlled pace that's pumped into an anaerobic tank. So now we're creating the food that the phosphorus-removing bacteria like to eat side stream in one place in a controlled manner. We're pumping it in at a constant rate or a controlled rate, and at least in theory, jump there and supposed to go nice and slow. The volatile fatty acids will be pumped into the anaerobic tank, and you'll have enough to supply the phosphorus-removing bacteria so that they will become energized. As they do release the phosphorus, you can measure the amount of phosphorus, soluble phosphorus, leaving that anaerobic tank and be broken down, or be that phosphorus that was released plus the phosphorus from the influent will be sucked out of solution in the aeration tank, leaving a very low phosphorus concentration. Same issue here with nitrogen interference. If there's nitrates, they're going to have their fill of the VFAs that are produced in that fermentation tank and pumped in. So the design engineering community came up with the idea of preceding that anaerobic tank with an anoxic tank. Same concept as I mentioned before. The nitrates in the return sludge in and with the mixed liquor will be removed using the BOD on the influent. the VFAs that are produced in the fermentation tank, a higher percentage of them will now be put to the intended purpose, which is to feed the phosphorus removing bacteria. So those are two designs. Of course, the more tanks, the more things going on, the better control you have, but there's more things to tend to. So let me say a couple words of process control, how to control those systems, and then we'll get into case studies. In fact, let me do this, and then I think we'll do that, what do you call it, polling question, and give everybody a break. So bear with me for maybe 5 minutes here, and then we'll take a good 5-minute break. How's that? So if you have a system and you've got it with an anaerobic tank, but it's not, you're not seeing 3 times the phosphorus coming out of that. Maybe you're seeing the same, or maybe half again as much as what came in. Well, then that anaerobic tank is not performing, right? So what do you do about that? Well, the simplest thing that I'll tell you, it's an energy-saving, more sustainable solution, but you turn off the mixers, and you run that tank 3-dimensionally. Allow solids to settle. More counterintuitive. We're not supposed to let settling happen. But now, on purpose, we're going to allow solids to settle in the bottom of this tank. What's going to happen? It's going to become more anaerobic in that tank. Certainly down in the sludge blanket. And then maybe even divert, put an elbow or chimney, a drop, to divert the flow down into that sludge blanket. Okay, that's going to mix it a little bit, but not so much as mechanical mixers. So now we have a more anaerobic zone, which will bolster its ability to create volatile fatty acids, so VFAs, and it'll make for a stronger anaerobic fermenting environment, which will help the volatile fatty acids, help them, not help them, hurts them, they're getting eaten, help the bacteria that eat the volatile fatty acids consume them. It's a tool that I've used many times, and particularly in plants not designed for phosphorus removal. We start creating dead zones on purpose, okay? Obviously, those dead zones need to be periodically resuspended. If they're allowed to be dead zones for too long, you're going to lose mixed liquor there. Your mixed liquor concentration will drop down to the detriment of the overall plant performance. And the solids will sit there so long that they start to decay and release phosphorus in a non-beneficial way. So can't turn them off and turn them on every 6 months. So maybe cycle them on once a day, every 6 hours, enough to resuspend the materials for a short period of time so that you don't lose all your solids, but for the majority of the time create a nice anaerobic condition. Okay, now what do you do if, okay, that isn't my problem. I'm getting the phosphorus release in the anaerobic tank, but my effluent still has high phosphorus. Well, there's 2 most likely possibilities for that. 2 causes, sources, 2 things that are going on. One, maybe your aeration tank, it isn't working. You're getting the phosphorus release in the anaerobic tank, but you're not getting the phosphorus uptake in the aeration tank. Well, that could be because you don't have enough oxygen, okay? If you're getting ammonia removal, then you'll probably have enough oxygen. More likely, it's a pH issue. The pH drops below that magic 6.8. It's like the curtain dropped on the performers. The show stopped. So the pH is a very likely possibility. I've seen situations, and particularly in Tennessee, where in warm weather, there's so little BOD finding its way into this aeration tank that there just isn't enough to grow the bacteria. So the conditions are right. If only there was a little more BOD, then the phosphorus removing bacteria that have the energy to drive it, but they don't have enough of the building blocks to make new cells, they're unable to grow as much as we'd like. And since they can't grow, they can't suck the phosphorus out of solution. The second total different problem is maybe you're getting great VFA production, uptake, removal, phosphorus release in the anaerobic tank. Maybe the aeration tank is working just perfectly for you. But then after you've removed all the soluble phosphorus, and this actually happened in the Athens, Tennessee, there's a Little Mouse Creek, which is an oxidation ditch facility. In the summertime months, they're seeing really low phosphorus concentrations going into the secondary clarifier, 0.2 kind of numbers, but coming out of the clarifier was over 1. More than 1 days this was observed. So it's possible, and particularly more so in warm weather than cold weather, because in warm weather, bacteria are more active. If there's a dead spot, if there's a high sludge blanket, if there's a low return sludge pumping rate, it's possible that you're getting a re-release somewhere after the aeration tank. Maybe there's a channel with a dead zone and some solids are settling out. And in this case, we need to mix the bejeebers out of that. Just the opposite of the cases where I do want it for solids. Now I don't want any solids settling once I've got this aeration tank and I got my soluble concentration real low. And I don't want it to have any solids anywhere settling out and dying, decaying, and releasing phosphorus in the solution. So how do you monitor that? You do profiles through the plant. Periodic facilities, larger facilities have strict limits. Once a week, they're running 3, 5, 6, 8 locations through the plant. They're getting a soluble phosphorus concentration, and they're monitoring it week to week just to make sure that all of their conditions are working, that their anaerobic condition tank's doing what it wants to do, the aeration tank's doing what they need, and they are not getting the re-release. Okay, one more. What do we have here? Okay, there we go. So optimizing it, I've got some rules of thumb here. And I think it's a good time for us to take our middle of the session break. We'll do our poll. I'm going to jump ahead. And there we go. So you can go ahead and set up the polling. And according to my clock, it's 6 minutes after. So let's have a break until, what do you think, 11 minutes after? Answer your poll, take a break, and if you have any questions or comments, type those in. Let's make it 12 after. Give you an extra minute. So,
all right, the poll is now open, so we'll work on that right now. And this poll is open for 5 minutes, so after those 5 minutes, we'll close it out, and I'll hand over you can take a look at it, the poll results, Grant, talk about it, and then I'll hand you over the presenter mode.
That sounds good. All right, thank you. Everybody enjoy your break.
All right, the poll is closed, and I believe it's displayed now.
Well, I can see it. Hopefully everybody else can. It looks like the majority of you work at facilities with 5 or more people. 3 of you folks are solo. 4, there's 2 of you. 2, there's 3 of you. 9, 4, 24 with 5 or more. So we're represented by, I guess, some of the larger, mostly facilities in Tennessee. Looks like I'm now the presenter again, so I can go back to my slides. I thought of a yes/no question. Oh, here, let me get back to put my video on. Yes/no. So yes are you getting snow now, or there's snow on the ground? And no, it's not snowing and there's no snow on the ground. And I'm not going to be able to see the answers. So, Mark, maybe if you could tell me what's the snow situation in Tennessee. I'm just curious.
Let's see here. No, I'm getting a lot of no's. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 yeses.
All right, so there isn't as much snow as what I thought.
Yeah, we have snow on the ground here in Middle Tennessee. Nothing coming down currently, but we should be getting another storm coming through tonight.
Oh, you are? Oh, man. Yes. All right, well, hopefully no power loss. That would be a more relevant question that we can, should we do that? If anybody lost power? Yes.
How many plants are running off generators? How about that?
Okay, how many of you are or did run on generator for a period of time? Yes would be you are or did run on a generator.
Looking like no one. 2. Maybe 1. Yeah, 2.
All right. Yeah, if they were run on generator, they probably wouldn't be with us right now.
Very true.
Thank you for those of you who are. And last count I saw there was somewhere between 60 and 70. So thank you. All right, now we're going to get creative, do one more little session, and then the last half hour we'll do case studies.
Make sure you remember to share your PowerPoint.
Oh, okay. I can do that. Thank you. Okay, I'm back. My screen is being shared, I hope. If not,
you're good to go.
Okay. Okay, so we have a facility not designed for phosphorus removal. This will be my last session with the phosphorus and then the case study. So I'm going to erase the design and kind of bring it back to more like maybe something close to what those of you watching have. So the most common, easiest way to try to make this machine into a phosphorus removing machine is to look to create a side stream fermenter. And the place to look is over there at that sludge storage tank, because that's got waste activated sludge. The gravity thickener, or whatever your primary sludge is, doesn't have the bacteria in your mixed liquor. See, that's before you get to the mixed liquor. So we want waste activated sludge. And we want to turn it, if it's a holding tank, or if it's an aerobic digester, we want to find a fat spot in the pipe, some kind of a vessel, where we can let the sludge sit for 2 or more days, long enough to get septic, long enough to create volatile fatty acids, long enough for any phosphorus removing bacteria that would live in and with that waste sludge to eat on those phosphorus, or to eat on the volatile fatty acids, and then pump some of that back into the aeration tank. And a rule of thumb I like to use is 10% of whatever your daily waste is. So if you're wasting, just to pick a number, 1,000 gallons a day, because I can do this in my head. So if you're wasting 1,000 gallons a day, then you want to return 1/10 of that, so 100 gallons a day back into the aeration tank. And that should be enough to drive phosphorus removal. The energized BioT bugs that come back into that aeration tank, once they hit the aerobic conditions, should suck phosphorus out of solution. Of course, now you're adding some sludge back into the aeration tanks, you're going to have to increase your wasting rate a little bit. But pretty good trick, and I'll give you some examples of where that worked in Tennessee. So unless there's any questions, let's get into the fun part. Look, in my case studies, now that I've done the background on nitrogen and phosphorus, kind of repeated what the first 2 sessions were, drove them home, bored somebody to death perhaps, hopefully it was of value to the majority of you. Let's talk about how some creative operators have applied themselves to milk more nutrient removal out of their facility. So I'm going to start with Cookeville. Cookeville is a pretty good size treatment plant. Got 4 great big oxidation ditches, one of which is hidden underneath that little banner. We'll pull it out from under that in a second. Cookeville was featured in the December TPO magazine. Here's a picture of the staff. Tom Graham in the center, John Buford, the tall guy with the ball cap, kind of the goatee to what's that? To his left. Those 2 are the key, and put a lot of good energies into changing their day-to-day operations, mindful of nutrient removal. It was reported, like I said, in the December TPO magazine. So they began in earnest in 2015, and you can see a rather dramatic, remarkable, beneficial drop in effluent nitrogen. Nitrogen had been averaging around, call it 15 milligrams per liter, and is now averaging below 5. So there's discharging 1/3 or maybe less than 1/3 as much nitrogen from a facility by operating it differently. Phosphorus, it's I call that a general downward trend. I think it's nowhere near as significant as the nitrogen removal, but a lot of things come out to me. You look at 2011 through 2015, and look at that seasonality. Midsummer, high numbers. Winter, low numbers. Midsummer, high numbers. Winter, low numbers. Midsummer, high numbers. And then, as they began working on the facility in 2015 and subsequent, more consistent, okay? Late 2019, consistent, not so much in a good way, but it started trending up. But much more, just looking at the data, you can see folks that are getting a better understanding, a better control, and I think the future is going to show continuous improvement in phosphorus removal there. Now, not shown in the graph is a very important thing, which is these efforts have reduced their electrical use by $250,000 a year. Okay? It's almost $1,000 a day. I haven't done the math. What is it, 750, 800 bucks a day? Somebody can do the math if you care. It's a big number. Less electricity, better effluent. Who would have thought? So here's how the facility's designed to work. Oh, we're going to focus on one of the ditches here. So there's 4 of these ditches. So same story times 4. Each ditch has 6 rotors, horizontal shaft, aeration rotors. We're up to 5 now. There's 6. 6 of them in that one ditch. All the other 3 ditches are just the same. So 6 times 4, there's 24 of these rotors designed to run all the time. Staff there made a number of trials. We did the trials before there were limits. So for those of you who do not yet have limits, well, I tell you, now is the time to make your trials because you're not going to violate a nitrogen limit if you don't yet have one. It gives you the time to see what you can do. The results here were so good that they considered themselves saving at least $4 million on a planned upgrade that they no longer need. So what are they doing? They run 2 of the rotors at a time instead of all 6. Run 2 of them side by side, run them for 4 hours. They run another pair side by side for 4 hours, and the final pair. What that allows is a strongly aerobic conditions downstream of the 2 rotors that are operating, and then a great big run of no oxygen to create that anoxic zone for nitrate removal. Any questions or comments on that? But then coming up. Go ahead.
Nothing in chat so far.
Okay. So for phosphorus removal, there's a belief, and I'm a supporter of this belief, is that downstream of the zone where the 2 rotors are running, they're getting some deposition. So there's a lower level of wastewater that's getting septic enough to create the volatile fatty acids. Some of the phosphorus-removing bacteria that are in and with the mixed liquor are falling into that sludge blanket. They're eating those volatile fatty acids. When that zone gets resuspended, it becomes aerobic, and they're getting phosphorus removal. All right? And I think what we saw from that graph is they're beginning to see a more consistent number year-round and starting to dial it in. I did just see a question pop up. The question asked, are they just doing it in the 1 of the 4? No, they're doing it in all 4. And I should have made that clear. Thank you for helping me with that. I just, for simplicity's sake, I picked 1 to show what's going on, but this is what's happening in all 4 of the ditches. They're operating all the same way. All right, any other questions or comments?
None in the Q&A.
All right. Let's go to North, another prize winner. Okay, so we had Cookville featured in TPO in December. Norris is right at the location, I think, probably gets the wastewater from the Appalachian Museum, right northeast of Knoxville, or north of Knoxville. Totally different facility. Let's talk about them. Pictures of a couple of our heroes here in the business. Tony Wilkerson on the left, Doug Nelson on the right. Their work resulted in a governor's award for their creative work at the Norris plant. like the Cookeville plant, Norris does not currently have a nitrogen or phosphorus limit, total nitrogen or total phosphorus limit, but in anticipation of it and in an effort to see what they could do with the equipment they have, they took it on themselves to operate their facility differently. Now, unfortunately, from a data crunching standpoint, we don't have data that precedes their efforts because they weren't even required to monitor for nitrogen. But this facility, as I'll show in a couple slides, was operated with the air on continuously as designed, and the nitrogen numbers were surely in the 20 or more milligrams per liter, and are now right in the 5 to 8 milligrams per liter. Phosphorus, real interesting here, and I really want to share the story on phosphorus removal. Look at that trend. Okay, it was started right around 4, and in the last 3 years now we're cut in half at 2. More of those low bars, low numbers, and fewer of the high numbers. And there certainly seems to be a trend. Had some high numbers in 2020. As they work through this, I think that they're going to get ever better numbers there. So let's talk about the facility. I'm sorry about the grainy picture, but it's a fairly small facility, and the resolution of the Google Maps was not maybe what we'd like, but they weren't thinking about us, were they? It's interesting. Notice the size of the pickup in this picture, and in future satellite pictures, you can get the scale of plant size by how big or how small the vehicles are in the picture. So this is a plate steel tank. It's a 1970s vintage. I noticed that Tony was signed in, so Tony, if I get anything wrong, which I'm sure to do, please correct me. I won't be embarrassed. I don't want to misspeak, but I'll give it my best here. So it's a plate steel Smith & Loveless facility. There's a donut on the outside, which is the aeration tank, and inside that donut is the clarifier. So wastewater that comes in and goes around this aeration tank. So what would you call that? A plug flow, extended aeration tank. And then the flow goes into the clarifier for settling. Now I want to point out your attention. If you go from the bottom of that arrow and continue outside, you see 2 white squares there. Hopefully you can see those. If I back up, if I were to turn that arrow around, they'd be pointing at what I'm trying to mention here. So there's 2 white squares. Those are chemical totes, looking like this. So the plant staff there found a couple of used chemical 300 gallon, 250, 75 gallon, I'm not sure which size they got, totes, maybe 350 even. But 2 of those chemical totes, and they waste sludge into it. The sludge sits there for a couple of days, maybe a little more, and then they drain that sludge back into the aeration tank. They've created a side stream fermenter for $100 that takes takes mixed liquor, lets it go septic. If it goes septic, creates volatile fatty acids. Because there's mixed liquor and phosphorus removing bacteria in there, they are consuming the volatile fatty acids. And then as they're released back into the aeration tank, they're taking up the phosphorus. So there's a $100 fix that to date has cut their phosphorus in half. Hence the governor's award. Any questions or comments on that? Tony, is there anything you'd like to add? You just raise your hand or unmute you, and you can talk for the next 15 minutes, and I think everybody would appreciate it. not. All right. Anybody else have any questions or comments? Two totally different approaches, two totally different technologies. Creativeness never would have happened without the operators applying themselves. And a lot of fun, right? Why do they do it? They do it because they care about their community, they care about the environment. But you know, it's kind of fun to outsmart the engineers and get stuff out of your facility that it wasn't designed to do. All right, let's take this to a much bigger scale. Unless there's any questions or comments. Hearing none, we're going to go to Nashville. Actually, I think this is in Madison, this facility, just to the east of Nashville, a little bit north maybe. It's Nashville's second biggest plant, 24 MGD facility. So we're going to concentrate on the aeration tank in my discussion. And in this case, there are 6 trains in there, 6 parallel trains. Like Cookville had 4, this one has 6. And I'm gonna talk about one train, and for their trial, they only did do it with one train. Excuse me. And since the trial involved only one train, the final effluent data, didn't change all that much. We saw some data during the month or two that they were doing the trial, but I don't have a good representation of data to show you. So we're going to focus the discussion on what they did, why, and what they were after. Now, inside each train, if you can see it good enough on the picture on your screen, let's take that top section inside that circle. You can see a darker spot with 2 little white dots in it, and then the rest of it looks a little different. That dark zone is a air-off zone. So this facility is designed with a selector. It's a really nifty idea. The idea was if you create a low oxygen zone followed by a high oxygen zone, that low oxygen zone is going to kill off the filaments that will thrive in the high oxygen zone. And that's really a benefit of, not universal, but in most cases, a benefit of changing your operations to one of these air on, air off. Oh, I didn't mention that, north. In the aeration tank for nitrogen removal, they're cycling that air on and off for an hour or 2 at a time on, hour or 2 off. My apologies for not mentioning that. Cycling the air on and off, or creating an air off zone, as is done here at Dry Creek, you create an environment. During the air on, it's going to select against the filaments that will grow in a low oxygen. And during the air off, you're going to create an environment that will select against the filaments that will grow in a high oxygen. So this plant was designed not really for phosphorus removal or nitrogen removal. It was designed to create a better settling sludge. Nice big air off zone. Well, in that air off zone, it works really nice as a fermenter. And consistently, Nashville Dry Creek produces a nice low effluent phosphorus. I don't recall the numbers offhand. Maybe if Jordan Fay or anybody who was working on this recalls, but I think it was around 0.5, 0.6 effluent phosphorus. Johnny McDonald of this facility, or David Tucker of Metro, they can help me with that number. But a consistently low phosphorus because that zone built into the facility. Well, during the study, we were trying, in one of the trains, we were trying to improve nitrogen removal. We did that by taking that whole aeration zone, the U-shaped tank, one train, so heads to the right and then turns around and comes back from right to left into that blue zone, and they cycled the air on and off. They had to do that manually, but it's staffed around the clock. They were literally having guys manually open and close the aeration valves in that zone several times a day. Didn't really do anything for us, except get people out into all kinds of weather to cycle valves. So we thought, well, it's a plug flow plant with all the flow coming in here. If we could maybe we're losing all of the BOD and there just isn't enough to drive the nitrate removal. So there is a step feed valve down at the far end. Hadn't been operated for a number of years, so that was a little problematic, but they worked through that and they opened that step feed valve so that a percentage of the flow, can't remember the percentages for several years ago, somewhere between a quarter and a third of the flow was being bypassed entirely around that first zone. The phosphorus went up a little bit because of that. Not a lot, but a little bit. And then this last zone, the air is cycled on and off. When they did that, I'm taking credit for it. When they did that, the total nitrogen in that zone declined, and looked to me like there was a measurable reduction in the electrical use, even though it was just one zone for that facility. So they were a great team to work with. It's a big facility. Most big facilities are hesitant to make changes like this. And they did. They had their engineering, their consultant, and their in-house engineers looking into it. And I think it had an influence on how Metro is looking to the future to solve their nutrient limits. Real beneficial results at a bigger plant. If there's anybody from Metro listening in or anybody from the Nashville field office that was involved wants to add anything to this, I'd sure welcome your comments. Not hearing anything. It looks like we have room for at least one more. This is another oxidation ditch. Harriman. And I tell you, credit goes to two people, and neither of them is me. Ray Freeman, who's the operator there now, and to TDEX John West. Is that right? Oh my God. John, a big guy out of the Nashville, out of the Knoxville office. Years ago, went out to Harriman and suggested, it is John West. Thank you, Corinne. So John went out there and talked to Ray's predecessor and suggested that they didn't need to operate this facility as designed, and that by taking a chance on a more creative way, they might get better results. So let's talk about what they did. Well, first the results. There's Ray, and there's that brilliant guy next to him learning from Ray. But look at the results down here. They cut their nitrogen over the years from over 25 parts to 2 parts. So that's just about 90% reduction. And the phosphorus cut in half. And an oxidation ditch by operating it different. All right. So here's how it's designed to operate. There's 6 rotors, or 4. Forgot where I was. There's 4 rotors, and they were designed to run all the time. Herman doesn't do that anymore. First John's advice, and they move slowly from 4 to I don't know what, but the current mode of operation is there's one rotor running, and then none. And then there's another, and then none. Another and none. I think you got the idea. So they're running with, instead of running 4 rotors 24/7, they're running no rotors, probably with almost as much as they have even just one rotor on. So a huge reduction in the amount of electricity used. What's that done? It's created a completely air-on environment when one of the rotors is on. The whole ditch goes aerobic, and then when the air is off, the whole ditch goes anaerobic. Now, Harriman, I believe, and Ray, if you're listening, I sure enjoy anything you have to offer, add into this thing, or if John is, if you'll forgive me, you can jump in too. But as they raise the mixed liquor concentration, this is what often happens as folks get into modifying their operations. And then once a day now, all the rotors come on one side. I've got all 4 of them coming on, but at one time of the day, both rotors will come on one side and run for a period of time. Another time of day, they'll come on the other side, staggered somewhat to resuspend the materials and create even stronger aerobic conditions. So what our current thinking is, and in the last few months, we've made an effort to really boost the dissolved oxygen for a short time of day in order to help, in order to create a time of day every day with a really strong aerobic condition, thinking maybe we can drop, or he can drop the phosphorus removal a bit more. So that's something that's ongoing, and we'll see what their success is. I just moved my camera over a little bit because I am seeing questions, but they're showing up right behind my camera. So one of the questions was, do I think, can we hope for better phosphorus removal in the future? Yes, I think so. I think Harriman, as is common with so many facilities, their sludge wasting is the tail wagging the dog, and I think that Ray is making ever more steps to improve his ability to waste sludge when he wants to waste sludge for process control purposes, and by boosting the dissolved oxygen for a period of time every day, I'm hoping that he can get that phosphorus to drop below 1. The other questions that came and went, I missed them, so Mark, if you wouldn't mind repeating, there was one fellow wrote a couple of questions, and I missed what those questions were.
Sure thing. Let me jump on it here. Let me get to that. Do you expect the phosphorus to drop even lower as 1? Don't know what that was related to.
And I think I handled that one.
Case studies involving round aeration ditches.
Round oxidation ditches. Yes, we're going to have some of those during our oxidation ditch discussion. So we will talk about the Athens, which has the orbital oxidation ditches, and some work that they've done in Athens, which I think would be my next case study coming right up. If people want to stick around and we can run over, I could do this. Talk about this one. Here's one with some orbital ditches. Is there any other questions or comments? And then you tell me if you want me to wrap it up or.
The only one other one was the ORPs and Harriman.
ORPs and Harriman. Okay. Ray is monitoring the ORP, and he's monitoring so that he has a positive ORP. I'm pretty sure I'm going out on a limb here to remember, but I think he's pretty close to those targets I talked about. I think during the air on, he's in the positive 125 to positive 150, and during the air off, the near surface water is minus 100. The very bottom of the ditch is very low. minus 200 minus 300, the bottom few inches where it settles out.
There was another question. They had initially asked about case studies with oxidation ditches, but they corrected that to say aeration basins, not ditches. So I think they're asking, are you going to have any case studies coming up dealing with just aeration basins?
I will. There's a whole section on conventional aeration and extended aeration. So yes, it will be dealing with plug flow and complete mixed aeration basins. We will get into that in a future. Well, which one is it? Let's jump ahead and see what's coming up. Yeah, it's a good segue into that. I'm going to go backwards here a little bit. So next week is going to be oxidation ditches. The week after is SBRs, and then March 10th would be inactivated sludge plant. I've got to make sure I put in acknowledgments. I got 2 pages of acknowledgments. And, the problem of doing acknowledgments is, you're going to leave somebody out that you should have put in there. But this whole effort of taking a treatment plant and dialing in the phosphorus and the nitrogen removal, it only happens because of the people. And, these presentations I'm given are on the back, so these people have done this work. Sure, I can throw out the ideas, and I do love throwing out the ideas and brainstorming, but then I drive away. And folks are left to make these ideas into products. So definitely want to acknowledge all of everyone. Shall we wrap it up here and do the last polling question and then do the exit surveys, and we'll be back again next week with what is it? Oxidation ditches, right?
Sure thing. I'll get the poll going right now. And we'll just let it run for a bit, and then I'll close it out.
And I'm going to sign off and thank you, the support team, and the entire audience for allowing me to speak to you again. And those of you who are taking it put up with me for one more time, I'll see you next week. How's that? Thank you.
Karina, I think you are signed in now. We had a question earlier asking about the presentations being posted on the TM Pop website. And do you have any idea when those are going to get posted onto the website?
Hello, we have a couple of them already posted, and as the PowerPoints are not hard to do, we can get them up there pretty quickly. On the video recordings, we have to do a file conversion, so as soon as we can get a file converted, it will be up there. So you already have 2 webinars there, and this one will be there within a week or so.
Yeah, please bear with us with the uploading. It does take some time, and it takes some time out of one of our employees because he can't touch his laptop for about 2 hours to upload. So we're working on it. We're working as fast as we can, and we'll try to get a quick turnaround on them, but it will take some time. Alrighty, I think that is it. Allie, I don't know if we want to close this out, stop the recording, if there's anything else, any other housekeeping we need to take care of.
Yeah, I'm just trying to figure out how to stop the recording, but I think we are good if everybody wants to sign out.
Well, awesome. Well, thank you all for attending, and once again, we appreciate you coming, and thank you so much for attending, even though we know that you guys got to be into work during these tough times with the winter. We appreciate everything that you do for us in Tennessee.